All right, everyone, buckle up, because today we are diving headfirst into the wild world of thermal physics. We're taking those A2 physics concepts and really cranking up the heat, if you will.
I think that's a great way to put it. It's incredible how these principles apply to everything around us, from the smallest atom to the largest star.
Absolutely. Let's start with something we experience every single day: heat transfer. You're making your morning coffee.
Please don't remind me, I haven't had mine yet.
Haha, right. But imagine that warmth radiating through your favorite mug. That right there is conduction, heat moving directly from one object to another.
Exactly. And the heat you feel just from being near that steaming cup, that's radiation, energy traveling in waves like light. And of course, we can't forget convection.
Oh, right, like when that hot coffee heats up the air above it, creating a mini current of warm air.
Precisely. It's this constant invisible dance of energy, always flowing from hotter objects to cooler ones, striving for sort of thermal equilibrium.
Fascinating. But what about temperature itself? It seems like such a basic concept, but what are we actually measuring when we talk about something being hot or cold?
Well, at its core, temperature is really just a measure of the average kinetic energy of the particles within a substance.
Kinetic energy, meaning their movement.
Exactly.
Hmm.
Think of it like this. The more those tiny molecules jiggle and vibrate, the hotter something is. It's like their excitement level.
So, in theory, if something were to reach absolute zero,
Absolute zero, the holy grail of cold. Theoretically, at that point, all molecular motion would completely stop.
everything would just freeze in place.
In essence, yes. It's 0 Kelvin, or about negative 273.15 degrees Celsius, a chilling thought indeed.
Brr, I feel a chill just thinking about it. But it's not just about how hot or cold something feels, right? These temperature changes can actually impact materials in fascinating ways.
Absolutely. Have you ever noticed how bridges, for example, have these gaps built into them?
Yeah, I always thought that was a bit strange.
Well, those gaps are there to accommodate for thermal expansion and contraction. In the summer, when it's hot, materials tend to expand, and in the winter, when it's cold, they contract. Those gaps ensure the bridge has room to breathe without causing damage.
That's really interesting. Another thing that always fascinated me about heat is latent heat. Like when ice is melting, it stays at a constant temperature, even though it's still absorbing heat energy.
Ah, yes, latent heat. That's a great example. You see, during a phase transition, like from solid ice to liquid water, the energy being absorbed isn't going into increasing the temperature, but rather into breaking those intermolecular bonds holding the molecules together.
So it's like the heat has a more important job to do, transforming the state of the matter before it can work on raising the temperature.
Exactly. We call this the latent heat of fusion. And similarly, when water boils and turns into vapor, that's the latent heat of vaporization doing its magic.
Amazing. And all of this ties back to that fundamental principle, the first law of thermodynamics, right?
Yeah. Precisely. The first law essentially states that energy cannot be created or destroyed, only transformed from one form to another. It's one of those universal truths, a cornerstone of physics.
So, like when you're using a microwave, the electrical energy is being transformed into electromagnetic radiation, which then heats up your food.
Exactly. Or when the sun's energy, light, and heat hit a solar panel and are transformed into electricity. Energy transformation is happening all around us constantly.
That's so cool. Now let's shift gears a bit and talk about ideal gases. It all starts with moles, doesn't it?
Yes and no. A mole is less about the gas itself and more about the quantity. It's like a chemist's counting unit, a very, very large one at that. We're talking 6.022 by 1023 particles, which is known as Avogadro's constant.
Wow, that's a lot of zeros.
It is. And whether we're talking about atoms, molecules, or those tiny particles bouncing around in the air, 1 mole of any substance will always have that many units.
Okay, so then how do those ideal gas laws we always hear about come into play?
Well, the ideal gas law, represented by the equation PV-nRT, elegantly summarizes how pressure, volume, the number of moles, and temperature all relate to each other in an ideal gas.
I'm going to be honest, equations aren't usually my thing, but I'm intrigued.
Huh? I understand. Think about it like this. Imagine you're pumping air into a bike tire. You're increasing the number of moles of air inside, U-hen, and that in turn increases the pressure P.
Because there are more particles trapped inside a confined space, so they're bumping into each other more?
You got it. And since the volume of the tire V doesn't really change, the temperature T has to increase to balance everything out.
Ah, that's why bike pumps feel warm after you use them.
Exactly. Of course, real gases in the real world are a bit messier than this idealized scenario. They don't always play by the rules, especially at extreme pressures or temperatures.
So how do we make sense of real gas behavior?
Well, that's where the kinetic theory of gases comes in handy. It helps us visualize gases as a collection of tiny particles, like billiard balls, constantly in motion, colliding with each other and the walls of their container.
And those collisions are what we experience as pressure.
Exactly. And the faster those particles are moving, the higher the temperature and the pressure.
It's amazing how all of these concepts, from simple heat transfer to the complex behavior of gases, are all interconnected.
It really is. It shows how these fundamental laws of physics govern our universe from the smallest scales to the largest.
It's quite a thought. So we've spent a lot of time discussing ideal gases, but how do those behaviors change with real gases in less than ideal conditions? That's something to think about. Until next time, happy learning, everyone.